All right. So we'll start a new section. And the goal of this section is basically to be more careful about loop diagrams, and in particular to show you what matching is between two effective field theories. We'll still be thinking in the context of massive particles. That's the simplest place to describe this, although we'll probably do an example later on of a case that doesn't just involve massive particles. So let's start out with a very trivial example just to see what we're talking about. So we'll take two particles. One of them is a heavy scalar. It has mass capital M, which I put a little underline so you can tell my capitals from my lowercase, because the light fermion that we're also going to have has a lowercase mass, little m. OK, so heavy scalar, light fermion. And so what we want to talk about here is really this picture that we described to you earlier, where we've got two theories, 1 and 2, and we want to pass from theory 1 to 2 by removing something from theory 1. So theory 1 here will be just the theory of these things, and we'll make it a renormalizable theory in the traditional sense, just so we know where to stop. And this guy should be capital. And then there's some Yukawa interaction between them. So we'll think of this as being the theory 1, where we're in a situation where capital M is much bigger than little m. So then we want to think about describing psi at low energies. And that means we can get rid of the scalar as an explicit degree of freedom. So low energies relative to this mass scale, which is heavy, M, capital M. We're going to remove the scalar from the theory. So you could just say remove it, or you could say integrate it out. When you say integrate out, the words you're using have a path integral connotation, where you have this in the path integral, and you think about just doing the path integral over that field and removing it. But the words of removing it or integrating it out are synonymous. So what's theory 2 going to look like? Well, we'll still have the kinetic term for our fermion. And then removing the scalar will generate some new operators. In particular, there'll be a dimension 6 operator like this. And then there could well be other terms. And so if we wanted to figure out what this dimension 6 operator is at tree level, that's a pretty straightforward exercise. We would simply think about the Feynman diagram in theory 1. So here's a Feynman diagram in theory 1 with Yukawa couplings here. We would calculate this Feynman diagram. And we would assume that all the momentum of the external particles are small. And that means that this is small. And we would just expand. And then we would just ask that when I take the Feynman rule from this, whoops, should have been a square there. When I take the Feynman rule from that, then I should get the same thing as the Feynman rule from that. And that will fix this coefficient A, which is so far arbitrary. But we can determine it by using theory 1. And that's the idea of doing a matching calculation, that you have introduced the theory 2. It has some parameters in front of operators. In this case, I called it A. And we want to determine those parameters by doing calculations in theory 1. And in particular, what you do is you make sure that S matrix elements in the two theories agree. But at tree level, that's just like matching up diagrams. So A is simply G squared. So we just have to match up this guy with that guy. And so taking the leading order term, A is just G squared. Very simple. So the place where this gets more involved and more where you have to think a little bit more, this seems like almost automatic, that you just do calculations in here and just match them up. And that's the basic idea. It's only a little more complicated when you have to take into account loops. So that's what we'll spend most of this section discussing, since this part is easier. So what about loops? What are some of the issues that come up there? Well, the first one is that the Feynman diagrams diverge, so you have to regulate them. And the thing that can be confusing about thinking about effective field theories and thinking about divergence diagrams is separating the ideas of regularization and the mass scale lambda nu that we've been talking about. So that's something I want to talk about in some detail. Because they're not the same thing. So we need to cut off ultraviolet divergences to obtain finite results. And that means we introduce cutoff parameters into our results. So examples would be taking the Minkowski momentum, continuing it to be Euclidean, and then just putting a hard cutoff on it. That's one example. Or you could use dim reg. That's another example. Or you could use a lattice spacing. That's another example. So these are all examples of how you might cut off the theory to remove ultraviolet divergences. And then there's a second step, renormalization, distinct from regularization. So some of the things I'm teaching you here should be familiar. And the only real generalization that we're going to do is we're going to be able to apply some of the things that you learned about renormalization and regularization to any operators that you might have in the theory, whether they're renormalizable in the dimension 4 traditional sense or in a higher dimensional sense. So here, what we're doing when we talk about renormalization is we're picking a scheme that gives precise or definite meaning to the parameters in the effective theory. Or even more explicitly, each coefficient in the Lagrangian, as well as the operators in the Lagrangian, are given a meaning by this procedure. If we didn't have a renormalization procedure, then because of the ultraviolet divergences, there would be ambiguities in how we define the coefficients and the operators. Or even if you don't have ultraviolet divergences, you still have freedom to pick different schemes for the definitions of the coefficients. And when you do this, you also can introduce parameters. So you can get parameters from regularization. You can also get parameters from this. So some examples that are familiar. There's this scale mu that shows up when you do MS bar. If you do something that's a little bit different, if you take Green's functions and you go to some off-shell point, that's another renormalization scheme called off-shell momentum subtraction. And that scheme also has a parameter that shows up. And if you did a Wilsonian renormalization, there would also be a cutoff associated to that. And this Wilsonian cutoff here doesn't have to be the same as this lambda UV cutoff. OK, so every coefficient, every operator, no matter the dimension, no matter where it turns up in the series, we're going to have to think about whether there's diagrams that generate ultraviolet divergences. And if those diagrams look like these operators, then you're going to get renormalization of those operators, and you're going to have to be careful about taking care of those divergences and also the scheme that you define the operators in. So you can think about this just as far as the coefficients are concerned. As starting out with some bare coefficients that depend on your ultraviolet regulator, and switching to some renormalized coefficients which don't depend on the ultraviolet regulator but do depend on the scheme. And then also you have some counter terms that depend on both things. So that's how it would look if you wrote that down for a cutoff in a Wilsonian sense. If you wrote it down in dimensional regularization, it would look like this. Same idea, different names for the parameters. OK, so in dimensional regularization, epsilon is the ultraviolet regulator, shows up in the bare coefficients. The renormalized ones don't depend on epsilon anymore, and these are your 1 over epsilon poles. All right. So one of the things that makes this tricky is when you start thinking about your power counting. And so I want to spend some few minutes talking about that. So let's consider this example that I wrote down with the 4 fermion operator. And if we just loop up the 4 fermion operator, then we can get mass renormalization. So this is psi dagger psi squared, and I'm sticking it in. And looping it up. So we start out with a tree level mass little m, but there's a 1 loop correction that involves one of our higher dimension operators. And there's some correction to the mass, which I'll call delta m. I'm not going to worry too much about the overall prefactor. This operator came with an a over m squared. And then there's a loop integral. There's a fermionic propagator, so that's a k slash plus m over k squared minus m squared. This guy here drops away. And really, we just have a correction that's a scalar, and that's a correction to the mass. Speak scalar in the spin space. So it's a little m over capital M, and then just this integral. And if we continue it to be Euclidean, then it looks like that. If we continue the from Minkowski to Euclidean. That's why I put the I there. So if we just assume that this integral that's sitting there, there's only one mass scale that it seems explicit there, the little m. So if we just assume that that integral is dominated by the scale m, little m, then you could do a power counting for this loop integral. You just assume that all the factors of k are of order little m. You've got an explicit little m, 4 powers in the numerator, 2 powers downstairs. So you would say that this integral scales like m squared. And then you would put that together with your delta m and say that delta m scales like a little m cubed capital M squared. And so this is something that would then be suppressed relative to the original tree-level contribution. It would be suppressed by perhaps some 4 pi's from the loop, but also little m squared over big M squared. So it would be a small correction, which is really what we would like to be the case when we're talking about some higher dimension operator that was supposed to be suppressed. We'd like it to be a small correction. All right. So does anyone have any idea what can go wrong with this argument? I mean, I've been kind of glib about it. I just said, if the integral is dominated by that. So the thing is that we have to be careful about our choice of regulator, because regulators also can introduce scales. So let's do this more carefully. So let's consider 2 different choices for the regulator. So we'll start out with just a cutoff, which seems very natural from an effective field theory point of view, that your theory is supposed to be only valid up to some scale. So why not just take and cut off the momentum explicitly above some scale? And you can think about that scale as being of order big M. So we just don't include any momenta that are higher than that scale in our loop integrals. So we're only integrating over the region in momentum space where the theory is supposed to be valid. Seems like a perfectly reasonable thing to do. So in this case, we can take this integral that has some angular parts to it as well as a radial part, decompose it into the radial piece and the angular piece. I'll give you a handout or I'll post a page of lecture notes that have all those fun formulas that are useful to remember but not fun to talk about for decomposing integrals in arbitrary dimensions into radial and angular pieces. So if we do that in this case, then the radial integral, we can cut off the radial integral with a hard cutoff lambda of uv. And just by dimensions, the d4k becomes ke times ke cubed. So this is the radial k now. And this integral we can do exactly there's a loop factor, 4 pi squared. There's a lambda uv squared. And then there's a logarithm. It goes like lambda uv squared over little m squared. There's 2 scales that are showing up, lambda uv and little m. The answer depends on both of them. And then we can start expanding, because little m is supposed to be much smaller than lambda uv. Let me pull out an am over 4 pi squared. So there would be a logarithmic term. There's this lambda uv squared over capital M squared if I put that factor in. And then there's some. So everything I'm writing in the square brackets here is dimensionless. This has the right dimensions of a mass. OK, so you can see that if I do this, it's not satisfying what I said over here. I'd like the correction to be m cubed over m squared. There are corrections that go like m cubed over m squared, like this one. These ones are even higher. But there's this term, and that's not a small correction. So for that particular piece, what you're finding is that your power counting, your naive power counting of the loop was wrong because there's a piece from k of order the cutoff that's contributing for that part of it. And that's why your naive scaling argument didn't work. Now, this is the bare result. And we have to go through the renormalization procedure. And so if we go through the renormalization procedure, you can think of that as taking a piece of the integral. So in a Wilsonian sense, you would take a piece of the integral and absorb it into the counter term. So as promised, the counter term depends on both lambda uv and lambda, and those are just explicitly. I'm cutting off the radial integral here. And that does improve things, because then I can lower this cutoff, make it smaller. And what is left would just be lambda squared over capital M squared and log of M squared over capital lambda squared. So I changed the lambda UVs up here into lambdas by that procedure. So when I renormalize the psi bar psi squared matrix element, there's a correction from that to the mass, and the renormalized thing would depend on this Wilsonian cutoff lambda. OK, but I'm not fully getting around the issue that I'm generating this type of term. So let's do it with a different regulator. Which is dimensional regularization. Let's see what happens. Using the MS bar scheme, same calculation. So again, split it into radial and angular parts. And I'll give you formulas for doing something like that. But I won't write them down in lecture. Actually, I think I will write one down a little later, but I'll give you a more complete set as a handout. So leaving over the radial integral, but regulating it dimensionally just means that instead of having this guy to the cube power, it's to the d minus 1. And there's some pieces here that depend on epsilon. And my convention for the entire course is that d is 4 minus 2 epsilon, not d minus epsilon. So again, this is an integral we can do exactly. get something like that. And then we can expand we get a 1 over epsilon pole. We get a logarithm. There's some constant as well. And then there's order epsilon pieces. So you should contrast this result here with the result we had over here. The order epsilon pieces are kind of like these terms. They're the terms that would go away if I took the cutoff here to infinity, lambda uv to infinity, or epsilon to 0. There's terms here that go like m cubed over m squared. That's like this term. And this term's not there. This 1 over epsilon is related to the log divergence. And this thing here is a power divergence. So the 1 over epsilon is related to this log of lambda uv. You should think of log of lambda uv as going to 1 over epsilon plus log of mu squared. But we don't see the power divergence in dimensional regularization in MS bar. OK, so what's happening is, from this result, we are getting something that's the size that we expected. By our power counting argument. The regularized result is the right size by power counting. The logarithm here is the same log as in A. With, if you like, a correspondence between mu and lambda. So we're seeing that logarithm there. We're just not seeing this term. And if we wanted to write down the MS bar counter term, some correction to the mass, it would go like am squared. The diagram would look like just the 1 over epsilon pole in MS bar. OK, so the two regulators seem to give us kind of similar results, but not exactly identical results. And the question is, how should I think about this? What's the right way of thinking about this extra term? So there's a language that people use in effective field theory and dimensional counting for the difference between thinking about doing a regularization of type A and type B. And what you say is that in type B, your regularization of the problem does not break the power counting. Which means that you can do power counting for regulated graphs prior to renormalizing them. But you can see that in case A, that would be problematic, because our naive power counting wouldn't have given us the right result. So what do we say about case A? Well, if case B didn't break the power counting, then case A does. But you can say something a little bit more positive about case A. And that is that when you think about case A, you should really you can set up the theory with renormalization conditions such that you can restore power counting in the renormalized graphs and renormalized couplings and renormalized operators. But you don't have power counting, explicit power counting, in just the regularized results. So you can think that I just take the Wilsonian cutoff small enough that I make that annoying term small. And order by order, I can do that. order by order in my loop expansion, order by order in my calculations. OK, so in some sense, there's nothing wrong with doing A. It's just that you have to work a little harder to think about it. And you have to, when you think about the power counting, you have to do that for the renormalized quantities, not for the bare quantities. So if you like, what you're doing here is you're adding counter terms. Another way you can say this is that you're adding counter terms to restore the power counting that you want. And that's not too different than you could always do that, actually. I've made this analogy that you should think about power counting as being related to, as being like kind of like gauge symmetry. So let's say you had a theory and it had nice gauge symmetry, but you picked some crazy regulator and broke gauge symmetry. Well, you could always put counter terms in that would break gauge symmetry and restore it in the renormalized quantity. That would be OK. It would be more work. We don't like to do that. We avoid it at all costs. But if we had to, we could do it. If you do supersymmetry, you might try to use dimensional regularization and supersymmetry. Standard dimensional regularization and supersymmetry breaks supersymmetry. If you do that, you have to introduce counter terms that restore supersymmetry. So the same language of symmetry is being applied here, except now to power counting, where we say that if your regulator messes up your power counting, you can restore it in the renormalized couplings. But you may be smart enough to think up a regulator, in this case dimensional regularization, where you don't have to deal with that complication. OK? So let me write that. So in an effective theory, you should think about regulating to preserve symmetries as well as to preserve power counting, if you can. And one way, in a more kind of formal language, that you could say what happens with the generation of that term that we talked about with the cutoff is that you mix up different orders in the expansion, and it looks like your naively higher order term is mixing back to a term of lower dimension. And so if you can get away with taking a regulator that doesn't have that mixing back to more relevant operators, then you could preserve your power counting, make it simpler. This is true irrespective of what the power counting is in. This is a general statement. In the context of what we've been talking about, which is dimensional power counting, there's a particular phrase that goes along with this. And that is that we talk about using a mass-independent regulator. Like dim-reg. It's, if you like, it has a mass scale, mu, but it's put in softly in a way that doesn't mess up power counting. We call that using a mass-independent regulator. So we want to avoid having different orders in the expansion mix up with each other. In general, I should comment then that terms that are the same order will definitely typically mix up with each other under renormalization. So even if you thought you were smart and you'd enumerated all the operators, but you missed one, and then you started calculating, that operator might just pop out at you because you could have some calculation with another operator mix into that operator. Or you could have an operator that you did a matching at tree level and you didn't generate, but then you start renormalizing that tree level operator, and another operator pops out at you. So it's important that you include all the operators that have the same dimension and the same quantum numbers, because if you don't include them, you're bound to get them from loops anyway, and you want to be complete. So if you like in a matrix type notation, you could say that the bare operators mix up with the set of possible renormalized operators, and there's some matrix of counterterms that would correct them, connect them. OK, so any questions so far? So sometimes in the literature, you'll see that these kinds of things, regulator discussions in effective field theory, generate all sorts of papers. Keep this in mind if you ever run into that. You should be able to think about the physics that you're after with different regulators and come to the same conclusion. And it just may be easier with one regulator versus another.